Let's see how quickly we can cover everything you need to know for GCSE Chemistry Paper 2 for Edexcel. This is good for higher and foundation tier, double combined and triple separate science. I'll tell you when some of the bigger concepts are for triple, but not what's for higher and foundation, as there's not a lot of difference honestly. And don't forget to check out the Science Shorts app to help you test your knowledge. Let's go. Electrons exist in shells around the nucleus. The shells fill up from the inside with a maximum of 2 electrons on the first shell, 8 on the second and 8 on the third shell, then we only go to 2 on the fourth shell. That's 20 electrons altogether, which brings us to a calcium atom. After this, we get into the transition metals, where things get a little bit crazy, so we leave that for A-level chemistry. So we only care about the electron configurations going up to 2882. Magnesium has 12 electrons, so its electron configuration must be 282. The periodic table can be split up into different bits. For example, everything to the left of this staircase is called a metal. Metal atoms always donate electrons when they bond to gain an empty outer shell of electrons. Again, transition metals are weird, but we don't think about their shells for now. To the right of the staircase, non-metals. They always accept electrons to gain a full outer shell. The column an atom is in is called its group. It tells you how many electrons an atom has in its outer shell. Again, the transition metals work in a really weird way, so they don't get their own groups. In fact, it turns out this is because they can donate a different number of electrons depending on what they're bonding to. The atoms in group 1 are called the alkali metals. They all have 1 electron in their outer shell, which they give away or donate when they bond to something, so they all have similar properties, like when they react with water. The further down the group you go, though, the further that outer electron is from the nucleus, so the electrostatic attraction is weaker between the negative electron and the positive nucleus. This means that the electron is more easily donated. This means the metals get more reactive as you go down the group. Group 7 are what we call the halogens. They're essentially the opposite. They have 7 electrons in their outer shell, so they need 1 more electron to gain a full outer shell. The further down the group you go, the less readily an electron is accepted onto that shell that's further away from the nucleus, so they get less reactive down the group. Their boiling points also increase down the group. Group 0, sometimes referred to as Group 8, are called the noble gases. They already have an empty or full outer shell, depending on your perspective, so they don't react. Well, in reality, sometimes they can react under special conditions, so we just say they're very unreactive. We don't really say Group 8 anymore though, because some people thought that helium might feel a little left out, as it only has 2 electrons in its outer shell. As electrons are negative themselves, metals become positively charged when they lose them. Metals always form positive ions. All of Group 1 lose 1 electron when they turn into an ion, so all of their ions are 1+, but again we don't write the 1, we just put plus. Group 2 lose 2 electrons to get an empty outer shell, so their ions are all 2+. Group 7 gain 1 electron each, so all of their ions are -1, just minus. Group 6 ions are all 2-. The atoms in Group 3, 4 and 5 don't really form ions, except for aluminium, which is 3+. Like we said, transition metals can donate different numbers of electrons. For example, an iron ion can be Fe2+, or Fe3+. It can donate 2 or 3 electrons depending on the situation. So we give the ions the name iron 2, the 2 in brackets, and iron 3 to distinguish between them. Transition metals are generally harder and less reactive than other metals. They also form coloured compounds. How fast a reaction happens is called the rate of reaction. Any rate is a change in a quantity divided by time. In chemistry's case, that could be the quantity of reactant used or product formed, or the effect that these have. So we could measure a change in mass or volume of gas that's made, or a colour change, for example. The boards, however, like to stipulate that this technically gives us mean rate, as the rate could be changing over the time you measure. But that's true for any measurement made over time ever, so that's a bit redundant, but we'll go with it. An experiment on this could be reacting hydrochloric acid and sodium thiosulfate in a conical flask sitting over a piece of paper with a cross drawn on it. As the reaction progresses, the product formed, it's a precipitate, turns the solution cloudy. We say the turbidity has increased. We stop the timer when we can no longer see the cross from above the flask. Repeat this at different temperatures, and you should see that the hotter the temperature, the less time it takes, so therefore the faster the rate. Another potential experiment is measuring the volume of gas produced by a reaction by using a gas syringe that fills up when it's connected to the reaction vessel. A graph to show this would have the quantity on the y-axis and time on the x-axis. It's usually a curve that starts off steep but then levels out or plateaus, which shows that the reaction has completed, or we can say reached its end point. To find the rate at any time, you draw a tangent at that point and find the gradient. Pro tip, turn the page so you're drawing the tangent horizontally. That will help you draw it accurately. Then, like the equation says, you can take the change in quantity and divide by time. Up divided by across, that's the gradient. The rate of reaction can be increased by the following: increasing the concentration of reactants if they're solutions, increasing the pressure of gas reactants, and increasing the surface area of solid reactants, that is, crushing them into a powder. Now, these three changes all have this effect because the reacting particles collide more frequently. They come across each other more often. Increasing temperature does that too due to the particles moving more quickly, but there's an added bonus that they also collide with more energy, meaning they're more likely to react when they collide, due to activation energy and all that. Finally, adding a catalyst also increases rate as it reduces the activation energy needed, so particles are more likely to collide successfully and react. Another slightly weird modern way of putting it is that a catalyst provides an alternative reaction pathway. Any catalyst is not used up in a reaction though. It's not a reactant or product itself. Any chemical reaction involves energy transfers, as energy is needed to break chemical bonds, while energy is released when chemical bonds form. Both of these happen in any reaction. If there's more energy released from bonds being made than energy needed to break bonds, we say this is a net energy released, and we should observe an increase in temperature as a result. This is an exothermic reaction. The way I think about it is explosions are exothermic. I mean, the X just means out in both words, doesn't it? If it's the other way around and there's a net energy input into the reaction should get colder. This is an endothermic reaction. We can do a practical on this. We carry out a neutralization reaction between an acid and alkali in a polystyrene cup, which is well insulated, and we put a thermometer poking through a lid that sits on top. We measure the maximum temperature the reaction reaches, then increase the volume of alkali used and repeat. Eventually, the maximum temperature won't get any higher due to all of the acid reacting, and the same amount of energy released is being spread across a larger volume of liquid. We can draw two lines of best fit for the rise and fall in these maximum temperatures, and where they meet tells us how much of the alkali was needed to neutralize the acid. We can use an energy profile to help us visualize the difference in energies between the reactants and the products. Now, this is something that people get confused with. The y-axis is technically potential energy, and you hopefully should know that usually in science, potential energy and kinetic energy do a balancing act. If one goes down, the other one goes up. So, if the potential energy of the product is less than the reactants, they must have gained kinetic energy, and that always means a higher temperature. So this must be an exothermic reaction. Just to reiterate, it might seem like the energy has gone down, but it's the potential energy that's gone down, so the kinetic energy has increased. Fuel must need a spark to start it burning, which is why we draw this bump to represent the activation energy, the energy needed to get a reaction started. Organic compounds are those that have carbon forming the backbone of the molecules. Crude oil can be found underground and is the result of plankton being buried underwater a long time ago. It consists of mostly hydrocarbons, that is, molecules made up of only carbon and hydrogen atoms. Most of these are alkanes, which are chains of single covalent bonded carbon atoms surrounded by hydrogen atoms. As such, there'll always be twice as many hydrogens as carbons in an alkane, plus another 2 hydrogens on the ends. We can therefore write a general formula for alkanes that's CnH2n plus 2. All alkane names end with ane, whereas the beginning of the name tells you how long the carbon chain length is. Meth is 1, eth is 2, prop is 3, bute is 4, hex is 6, and that's pretty much the highest you'll probably go to. Crude oil isn't useful as a mixture of all of these different length alkanes, so we use fractional distillation to separate them out. We heat them so they evaporate and rise up the fractionating column, apart from the very longest ones which stay as liquid, generally used as bitumen on roads. The column gets cooler the higher up the gases rise. As different length alkanes have different boiling points, they condense back into liquids at different heights, where they're then collected. Longer alkanes have higher boiling points because there are stronger intermolecular forces between them, which require more energy to overcome. The shortest alkanes remain as a gas even at the top. We can call this fraction refinery gases, or LPG, liquid petroleum gas, because they're put into pressurized containers to transport, and that turns them into a liquid. LPG contains a range of chain length alkanes, like all the fractions. In LPG's case, that's up to 4 carbons long. These are the other fractions you need to know. Petrol is the next longest fraction, so it condenses just below LPG. That's used in cars, of course. Kerosene is used for jet fuel. Diesel oil, used for cars and lorries and other things. And heavy fuel oil is used in large ships. As you can see, these alkanes can be burned as fuel. Longer fractions are more viscous or have higher viscosity, just a scientific way of saying thicker or more gloopy. Shorter fractions are more flammable, but these fractions can also be used to make solvents, lubricants, detergents, and perhaps most importantly, polymers used for plastics. Polymers can be made from alkenes, but not alkanes. An alkene is a hydrocarbon that has a carbon-carbon double bond in it. By the way, we call this C double bond C a functional group. Because of this double bond, we can also say that alkenes are unsaturated, whereas alkanes are saturated, which essentially means that they're full. That's why you can test for an alkene, which is a colorless liquid, by adding bromine water, which is an orangey brown. If the mixture turns colorless, that means that the bromine has bonded to the alkene. For example, it bonds to ethene by breaking that double bond into single bonds used to attach the bromines. This product is saturated, as you can hopefully see. This can't happen with an alkane, as it's already saturated, of course, so it stays orange. Chlorine and iodine do a similar thing, but water can also saturate an alkene by attaching itself as an H and an OH functional group. We've now made an alcohol, by the way. Now, there are 2 more problems with crude oil. One is that the demand for shorter alkanes is much higher than that for longer ones. Also, there aren't enough alkenes in it for our purposes. Cracking solves both of these problems, that is, breaking apart a longer alkane into a shorter alkane and an alkene. Catalytic cracking requires a temperature of around 550 degrees C and a catalyst called zeolite. If there's no catalyst, you can just use an even higher temperature of over 800 degrees. This is called steam cracking. Let's take butane and crack it. We can split it right down the middle, but it must be the same number of all types of atoms in the products. That means, yes, we make ethane, but we don't have enough hydrogen atoms to make another ethane, so instead it makes ethene as well, the alkene, which then of course is useful for making polymers. It could also split here instead to make methane and propane. The composition of gases in the Earth's atmosphere has changed over the course of its history. Records only go so far, so we have to extrapolate to get an idea of what it used to be like. To begin with, it likely was a lot of nitrogen and carbon dioxide. These then would have dissolved into the oceans, which were the result of water vapor from volcanoes condensing. Carbon dioxide would have then been trapped in sedimentary rocks and fossil fuels, reducing the carbon dioxide in the atmosphere. Algae and plants turn CO2 into oxygen through photosynthesis, and we now have about 0.03% CO2 in our atmosphere. Water vapor, carbon dioxide and methane absorb longer wavelength radiation to keep the Earth warm. This is the greenhouse effect. Without this, we'd freeze. CO2 levels have increased since the Industrial Revolution, which many think is responsible for the increase in global temperatures. I'm old enough to remember when the term carbon footprint was coined in the mid-2000s, and everybody went mad for it. It's the idea that everything you do is responsible for carbon dioxide being released into the atmosphere, and that we should reduce that or offset it by planting trees, for example. Carbon monoxide is an atmospheric pollutant. It binds to your red blood cells, so less oxygen can be transported around your body. It's also odorless and colorless, so it's hard to detect, and that can be fatal. Most fossil fuels release sulfur dioxide when burned, which causes acid rain. Nitrogen oxides can also be released, which can cause breathing problems. Soot is just particulates of carbon made from incomplete combustion, and they can also cause health issues. If we think we have hydrogen in a test tube, we can test for this by holding a burning splint over the test tube, and it'll produce a squeaky pop if it is. Oxygen will relight a glowing splint. Carbon dioxide will turn lime water cloudy when bubbled through it. Chlorine gas will bleach damp blue litmus paper, that means turn it white. We can test for some metals using flame tests. Lithium will produce a crimson flame, sodium yellow, potassium lilac, calcium orange red, and copper green. We can also test for some metals in solutions by adding sodium hydroxide. If aluminium, calcium, or magnesium are in the solution, a white precipitate will be formed. However, if it's aluminium, the aluminium hydroxide produced will then dissolve if excess sodium hydroxide is added. Copper 2 ions, that is Cu2 plus ions, form a blue precipitate. Iron 2, green precipitate. Iron 3, brown. You might have to complete an ionic equation for these, for example the copper and hydroxide ions making copper hydroxide, and you have to make sure it's balanced too. Carbonates react with acids to make carbon dioxide gas, and we can use lime water to test for that. We test for halide ions, that's halogen ions, by mixing with silver nitrate solution and nitric acid. If chloride ions are present, silver chloride is made, that's a white precipitate. If it's bromide ions, silver bromide is made, that's cream. Silver iodide, yellow. Finally, sulfate ions will produce a white precipitate when mixed with barium chloride and hydrochloric acid. In proper labs with lots of money, they use instrumental methods to determine what substances they have. These instruments are accurate, sensitive, and fast. For example, they can do flame emission spectroscopy, flame tests on steroids. The light produced by a flame is passed through a spectroscope, which can identify exactly what wavelengths are emitted, which can then be used to identify these metal ions. An alcohol is an organic compound with an OH functional group. Their names always end with ol, so this is ethanol. These can react with oxygen, that is combust, to make carbon dioxide and water if it's complete combustion, and carbon monoxide, or just carbon, soot and water if it's incomplete combustion, when there's less oxygen available. Short alcohols like ethanol can mix with water to produce a solution, which gets more difficult as they get longer. When an alcohol is oxidized without combustion, that is, with an oxidizing agent, it makes a carboxylic acid. That's a molecule with, instead of just OH, it's COOH. That's the functional group. We have that extra oxygen double bonded to the carbon. It still has the OH group, but it's not an alcohol anymore. The specific name of this one would be ethanoic acid, which is actually vinegar. You can also get propanoic, butanoic acid, etc. Polymers are super long chain alkanes made up of repeating sections made from monomers. Poly just means lots, mono just means one. For example, lots of ethenes, that's our monomer here, can be joined together through addition polymerization to make polyethene, or we just call it polythene. That's the polymer. These monomers must have a double bond in them. Note that even though it makes a long alkane, we still use the name of the alkene it's made from for the name. It's polyethene, not polyethane. As you can see, this happens because the double bond splits so a carbon can bond to the next monomer, and so on. Thankfully, we only have to draw the repeating unit with brackets around it and the bonds coming out with an N on the outside, showing that there are lots of these joined together. Condensation polymerization, on the other hand, is when we join together two different monomers that have different functional groups, for example, an alcohol and carboxylic acid. First, let's look at the bog standard reaction between just ethanol and ethanoic acid. These react to produce ethyl ethanoate. This is now an ester. Can you see water, H2O, must be kicked out? Now let's react an alcohol that has the hydroxide, that's the OH functional group on both ends, with a carboxylic acid that has COOH, we call that the carboxyl group on both ends too. Now this reaction happens on both ends and we can make a chain of this ester. This would then be a polyester. It doesn't really matter what's in between the functional groups, we can just write R as a shorthand for the stuff in the middle, or just a box. Again, water is chucked out, hence why it's called condensation polymerization. Polymers can be high density or low density. For example, you might see HDPE or LDPE on plastic bottles. They stand for high and low density polyethylene. Thermosoftening polymers melt when heated, whereas thermosetting polymers don't melt, no matter how hot they get. The difference is that with a thermosetting polymer, there are cross-links between the polymer chains that are formed when it's made. This increases the forces between them, holding them together strongly. Giant covalent bonding is similar to the lattice nature of ionic compounds. Atoms form covalent bonds to other atoms, which form bonds to other atoms, and so on, until what we have in effect is one giant molecule. Diamond is an example of this. It's a crystal of carbon atoms bonded to each other. That's why it's so hard and has such a high melting point. You'd have to break the covalent bonds in order to change it, and they're incredibly strong. Graphite consists of layers of carbons with 3 covalent bonds each in a hexagonal structure. Where's the carbon's fourth bond, you might ask? Well, the spare delocalized electrons form special weak bonds between the layers, which means that this can actually conduct electricity because the electrons can move between the layers. And it also means the layers can slide over each other easily too, which is why it's used for pencils. As a side note, it's the opposite with metal alloys. They're stronger than pure metals because having mixtures of different metals means we have different size atoms, and that disrupts the regular lattice, so layers can't slide over each other as easily. Back to carbon allotropes. Graphene is just a single layer of graphite. Fullerenes are 3D structures of carbon atoms. For example, Buckminster fullerene is a spherical football-like structure consisting of 60 carbon atoms. Fullerenes that have a tube shape are called nanotubes. Surface to volume ratio is just 1 divided by the other. If the length of a side of a cube doubles, this ratio halves. As nanoparticles are tiny, this ratio is huge for them, which means that fewer of them could be needed to fulfill a purpose compared to larger ones. Most glass we use is soda-lime glass, made from heating sand, sodium carbonate and limestone. Borosilicate glass, on the other hand, has a higher melting point. Ceramics, like pottery and bricks, are made from clay, then they're heated in a furnace. Composites are made from two materials, usually involving fibres of one material being bound around another. An example of this is carbon fibre, very strong yet light. So I hope you found that helpful. Leave a like and a comment if you did, and click on the card to take you to the playlist for all of the papers, and don't forget to check out the Quiz Shorts app to help you test your knowledge, and I'll see you next time.